Okay, so welcome to Math 219. The very first thing I need to say is we are recording. I've been recording all of my in-class meetings since like 2015 or 2014 or something. And so anyway, FYI, you've been officially informed. We are recording. And I'm going to hop now into the talk. First, before we get into any math, I want to revisit this page. Y'all have seen all of this before in the recording that I asked y'all to watch. I initially had on WarpWire. Seems not to have worked. I don't know why, but it's on YouTube. It's all visible there. Anyway, I'm not going to go through all of this again because, it'd take a long time. But I want to hit certain very important highlights. First, these two Sakai sites. Keep in mind there's a separate one for the course. The course policies involving all sections, and then there's a separate one for just my sections, right? So make sure to read all of those sites. There's a bunch of, tedious and boring information that all has to get documented. It's all important. It's how the class works, procedures and policies and stuff like that. So anyway, make sure to read through all of that and make sure you know how it works. If you have any questions, come to my office hours. Grab me after class, whatever is most convenient, and I'll be happy to clarify. Okay, next thing. I want to talk about course grades. And again, all the details we talked through in that recording, so I won't repeat them again. But what I want to say here is, first of all, make sure that you understand all the details about how course grades are going to be computed. But if you're confused about something, no problem. Come talk to me. I'll be very happy to clarify. Again, you can ask me after class, you can ask me in office hours, either is fine. But please don't just stay confused about it. I'm very sure that I can resolve any clarity problems that you might have. Just come ask me, happy to do it. Okay, last real quick thing I want to say is, y'all heard me give this whole speech about, what this course is about. Fundamentally, this is a course about ideas. Right? This is not a course about answers or numbers or, rote facts. Right? So I just want to hit this again that this is really important. That, this is fundamentally what the class is about. So unavoidably, yes, you will need to know certain equations and definitions and, what certain words mean and, certain algorithms you need to be able to execute. Yeah, sure. Of course. Right? But that is all in service of understanding ideas, right? And the ideas are the end goal. The ideas are ultimately what the class is really about. So keep that in mind while you're in class. You're going to try to focus on understanding the ideas, the details of the formulas, or memorizing the formula. These are details that you can deal with later, right? I'm going to focus on ideas. Likewise, when you're working on homework exercises. Try to think in terms of communicating ideas in writing. And again, this is a hard thing. This is a skill that has to be developed. How to take ideas that are in your head and communicate them clearly, right? And this is non-trivial. So homework is a great place to practice that. And then, of course, don't be surprised that problem solving on the exams is going to involve understanding ideas. Right? And so the exam questions are not going to be, here, execute algorithm number 42. Right? It's going to be, here's a problem, and you got to figure it out. And the way you're going to figure it out, the primary tool you're going to use to figure it out is to understand from the statement of the question, what are the necessary ideas, use the ideas that you understand from class and apply and adapt appropriately, etc. It's all about the ideas. Okay. All right. So, I'm going to pause there. Does anybody have any questions about any of that? Or anything from the recording, from the class recording that y'all watched on YouTube? Yes,
just
please.
A quick question.
Yeah.
So on the recording, there were a few numbers of exercises that we should do. Is that the homework or on the grade scope, or is that? So
you're talking about this right here?
Yeah.
Yeah. Okay. So this is what we call the content syllabus, and the content syllabus defines what will eventually be on a homework assignment, right? Now, what is on a particular homework assignment comes also from, there we go, okay, the lecture schedule that's on the section site. So for homework 1, right, you're going to look in these 3 green boxes. They're currently empty. I'm sorry?
They'll just have it written in
Yeah, it'll say like so. For example, today, based on the fact that in my first two sections I haven't documented for the second one yet, but I got through page 3, which ends section 1.6. So my fingers crossed plan for today is that this cell right here will say 1.6, and that being 1.6 defines that as part of homework 1, you should do all of the 1.6 exercises listed here, which will be those exercises. Yeah. Does that make sense?
Yeah.
And then, of course, there's also Friday and there's also next Wednesday. So I'm expecting it'll be 1.6 there, and it'll be 1.1, 1.2 here, and then probably 1.3, 1.4, something like that. So all of that will be part of homework 1. Cool. Anybody else? Does that all make sense? Is everybody? Yes.
Do those exercises come specifically from the book itself?
Most of them are in the book. There are some that are part of what I call the additional homework problems. So you see the AHP right here, right? So all of the exercises listed there. So AHP 1, 2, 3, 4 come from a file that's in the resources section. I'll just click over to it over here in the resources section, and let me go into student mode so I don't expose all of the secret stuff that I have here. Exactly. So right there you go, 219 AHP. So that's a PDF file with a bunch of supplemental exercises. I mean, the book is a really good book, by the way. I do like the book a lot, but it has a couple of gaps in the exercises, important topics that I feel like students need to see. Yeah. Okay, good stuff. Anybody else? Everybody's good. Okay. All right, so we're going to do a little bit of math now. Before we get into the book math, I want to address the general question of why is multivariable calculus important? Said differently, why are you taking this class? And for a lot of students, the answer is because my major requires me to, right? So I recognize that, no problem, but then let's ask the obvious next question, why does your major require you to, right? So now I think y'all are already sold on the idea that single variable calculus is important. This is a pretty easy pitch to make to students who have taken single variable calculus. The world is full of things that are changing. How do you understand change of quantifiable things? Well, those derivatives. That's one of the most important concepts in understanding the world is how are things changing. So it's a real easy pitch there, I believe. Of course, the other big object of study in single variable calculus is integrals. There is a common, I'm going to say, in my opinion, misunderstanding of why we care about integrals. Integrals are very often presented as a tool for computing the area under a curve. I suppose technically, but ultimately, when you get right down to it, very rarely do we actually need to compute area under a curve. Area under a curve is a convenient, fairly useless example of what you can do with integrals. And it is a visual aid to help us in understanding what we're computing when we're not really interested in area under a curve. But ultimately, what we really care about, the big applications of integrals, is computing what I like to call accumulating quantities. And so these are things like mass, for example. A classical example is you have a one-dimensional rod. I'm sure you've all seen this in Calc 1 classes. One-dimensional rod. So the mass is per unit length. And maybe it's more dense on this side and less dense on this side because of the alloy mixture varies or whatever. Total mass of the entire rod, how would you compute that? You can't multiply mass per unit length times length because it's not constant, it varies wildly. So what do you do? Well, you chop it up into little pieces, and the very first aspect of redefining that question as an integral is to say the total mass is the sum of the little itty-bitty masses of the individual pieces. So that's what I mean by saying an accumulating quantity. It's a quantity where the whole is the sum of the parts. And a lot of quantities are accumulating quantities. To be fair, not everything. Right? Perimeter, for example, is not an accumulating quantity. If you really think about it, you have a thing, it's got a perimeter. If you chop it up into a million little pieces and you add up the perimeters of all those little pieces, it's not the same thing. Okay, anyway, accumulating quantities are what we really care about with integrals. Computing things like mass and work and population, whatever. Lots of accumulating quantities in the world. Okay, so again, ultimately a fairly easy pitch that single variable calculus is important. So why multivariable calculus? Short version, because the world is not one-dimensional. The world's three-dimensional, right? I mean, this is pretty clear. So the following examples here are, I've chosen these examples because they're so simple, not because they're so necessarily so critical. But easy examples here. So let's start off by supposing that temperature is a function of position in space. All right, so we've got a three-dimensional world here. We're in a three-dimensional room here. The temperature in this room is not a constant. It's warmer by wherever the heat's coming out. It's colder probably by the windows. It's warmer next to the human bodies, colder next to the metal table legs. Right? So there's a varying temperature in this room. Suppose that you're sitting here and that you're moving with some velocity in some, kind of random direction, not exactly parallel to one of the axes. How would you find, given that, how would you compute how fast temperature is changing as you are at that purple point and moving with that blue velocity? How would you compute how fast temperature is changing? This is not a single variable calculus problem, right? I can't just say, well, take the derivative. Derivative with respect to what? Right? The temperature is a function of three different variables. Wow. It's not clear how we're going to go about solving this problem. Right? But fundamentally, though, you see how the fact that the world is three-dimensional is what makes this a hard problem. Right? This three-dimensionality of it. And one-dimensional examples, look, sure, to be fair, there are plenty of real-world scenarios where everything just lines up perfectly. We make a lot of simplifications and assumptions that suppose that, temperature is a function of only one of the variables or something like that. In which case, yeah, sure. But most of the time, it's not simple, and all the variables matter. How do you account for that? So, first, like I say, real easy pitch on why we need multivariable calculus. Simple stories like this. Here's a an integrally instead of derivative-y kind of example. Suppose instead of a one-dimensional rod, suppose you are looking at a three-dimensional lump, rock or whatever that is. And suppose that the density depends on all of the variables of position. Right? So if you think about it, this is actually pretty reasonable. If you have some rock that you find out in your backyard, well, it might be mostly sedimentary on one part of it, then it might kind of have one of those volcanic little sections in the middle, which is less heavy, and then maybe it has an ore kind of irony kind of section over on the other side. The density could easily be non-constant, right? So I'm going to represent that here by, there's low density, then maybe there's more density over on this side, and maybe it's really dense over on the far right. Oh, and then maybe it's also really dense, also kind of there. Right? Highly variable density. How are you going to compute the mass? The single variable calculus doesn't work here because the density, what eventually is going to be our integrand, is not a function of a single variable. So single variable calculus losing. And again, ultimately because the world is three-dimensional. This is a three-dimensional rock. It needs a multivariable integral, whatever that means. Right? We're going to have to adapt the idea of integration to a three-dimensional context in order to make sense out of this. So again, not that this is a deep problem, but This is a really, I like to think of, hey, how much faster is it getting warmer, and how much does that rock weigh, as being really relatable, relatively simple kinds of questions. And already, you see, we need multivariable calculus. How are we doing? Is everybody with me? Feel free to ask a question if you have any. Everybody's good? Okay, now I'm going to give you some more sophisticated examples specific to certain fields of study. And I think y'all are probably already aware that that multivariable calculus, math in general, is useful in things like physics. But so for with that in mind, I'm going to start with something that's totally different. I'm going to start with an econ example. Right. So now I made up this equation, but the point is that the exact details of the equation are not what we're interested in here. But what we're interested in is the fact that equations, kind of like this, are representative of how economists make models. So there's various objects of interest. Maybe price, quantity, interest rate, capital, labor, just for example. These are things that might be relevant in modeling some economic scenario. And what economists do is what they don't do is just write down P equals, because they don't know how to do that. That's often much harder. It's not clear what P should equal. What is clear are things like, these different variables contribute to certain invariants in certain ways. And so grand total, all of these things together, they have to add up to something that's fixed and not allowed to change. And so you can write down a relationship very often, something like this. You can write down a relationship between variables, even if you can't write down what any of the individual variables are. So that's just the nature of the beast. It's too bad that this is the way it is, but this is the way it is. So, reasonable question then: if this is your model, and you find yourself looking at some of these variables changing. By the way, this can come in several different forms. It could be that you've empirically determined that these variables have changed by certain amounts over certain amounts of time, just measurements. Yeah. Or it could be that you're considering a hypothetical scenario of, hey, I wonder what would happen if L were to be increasing at a certain rate, K were decreasing at a certain rate, whatever. Anyway, on the assumption that certain of these variables change in certain ways, reasonable question to ask: how does P have to change in order to keep this equation happy? Right? I mean, you can't just take an equation that works and then just start fiddling with some of the variables. The equation is going to not work anymore if you change some of the inputs. So if you change these variables, then you're going to have to change P in such a way as to sort of accommodate for that. So given these green rates of change, how am I going to figure out what the blue rate of change of P is? So this is a very natural, I'm going to say kind of basic sort of example of, how economists need to use math. And notice, this is a calculus problem, but notice further, it is a multivariable calculus problem, unavoidably, because look at all these variables. We've got, in fact, 5 variables that we're keeping track of, and furthermore, we're keeping track of how they change with respect to time, which is another variable altogether. Then we have 6 variables. And it's just not a single variable calculus problem. Everybody good? Okay, so if you're an econ major, you really need to understand multivariable calculus in order to deal with mathematical models. Okay. I like to take a nice little aside here as well and address another. I like to think of it as a mistake, but anyway, a lot of people think that you can kind of limit your attention to 3 dimensions. After all, we live in a 3-dimensional world, right? We've got X, Y, Z. What else is there? There is no. I'm not going to say there isn't a 4th dimension, but we certainly can't point in the fourth dimension. I have no awareness of a fourth. If I were to restrict my attention to the three-dimensional universe that I can perceive, one would think I'm probably mostly good, right? This is not a Doctor Strange movie. There's no time travel here. Seems like 3 dimensions ought to be enough. Well, my counter-argument to that is not all dimensions represent coordinates in physical space. Sometimes you're dealing with variables representing just other quantities that aren't coordinates. And you could easily have more than 3. So this simple econ example, as a case in point, we're doing math in 6 dimensions when we're doing this example here. I can't draw a picture of it, right? And I certainly can't visualize what it looks like in 6 dimensions. That's out of the question. But I can do algebra in 6 dimensions, and it's not that different from doing algebra in 2 or 3 dimensions. So anyway, that's just a little heads up. That said, yet most of what we're going to do in this class, we are going to mostly focus, I'll say, on 2 and 3 dimensions. But for whatever it's worth, a lot of what we're going to do, even though we're going to mostly do it in 3 dimensions, most of what we're going to do works just as well in 6 dimensions or 17 dimensions or whatever. Not all. Some of it's peculiar to 2 or 3 specifically. But most of it generalizes. Okay, how are we doing? Everybody happy? Okay, scary physics examples. Yeah, I know, exactly. Yeah. So, if you're a physics major, you're gonna drown in this stuff here. If you're an engineering major, to some extent also. But these are called Maxwell's equations, and these are a large part of understanding how electricity and magnetism work. If you've already taken a class in E&M, then you know what I'm talking about. If you have not yet taken a class in E&M, well, good news. What we're going to do in this multivariable calculus class will give you a massive leg up when you do take an E&M class. It makes a tremendous difference. So anyway, let's talk about these equations. Obviously, there's a lot to understand here. We're nowhere near ready to understand this stuff yet, by the way. Right? I haven't told you what any of this stuff means here. And what is that right there? Well, I mean, y'all have seen the integral symbol. You've probably never seen 3 in a row before. What does that mean? Well, we'll talk about it. Nothing to worry about. Here's a weird aspect of what we're doing there. There is what appears to be a differential, except it's a vector. What does that mean? Right? So there's some objects that we need to understand before we can make sense out of these equations. But I want to emphasize, we don't just want to understand what these objects refer to. We also are going to want to understand, why is this true? Right? This statement, whatever it says. Why is this true? And furthermore, understanding why it's true, what does that allow me to then further understand about electric fields? And there's some great answers to this question. The fact that this equation is true allows us to make a deeply powerful interpretation of how electric fields look and how they relate to charge density. And, what does electric charge do? What does it look like on the resulting electric field when you have more or less electric charge? So that's the kind of thing that we're going to be interested in. So again, it's not just a matter of knowing the definition of this and knowing the definition of this and knowing that these two things are equal. Those are, relatively rote things, but we want to know, why is this true and what does that tell us about the objects in play? Okay. All right, so punchline. Multivariable calculus is going to be really, really important if you're studying physics or engineering. And this is just one of the many examples of how multivariable calculus is useful. How are we doing? Everybody with me? Many, many, many details to follow. Oh, one other thing I should mention. You see 8 equations here. People commonly refer to Maxwell's 4 equations. In fact, physicists usually refer to these 2 equations as being pretty much the same equation. Now, at a glance, it doesn't look like it, right? They look pretty darn different. So how is it that these are, pretty much the same equation? Well, there's some interpretations that can be made of triple integrals. This is something called a vector surface integral. And what does this thing here mean? It's called divergence. How does that relate to these objects? And when you understand all the related ideas, we're going to be able to make a very natural and pithy interpretation of why it is that it's really very natural to refer to these as being different versions of ultimately the same statement. And so that's another goal to have in mind when we get to this much later in the course. Why are these two equations morally the same? Okay, all right. So lots of ideas that we need to develop, and likewise, of course, pairwise going down. So these are the four equations. All right. Now this one we're not going to study in Math 219, but I want to bring it up anyway. It has it very naturally relates to chemistry in addition to physics. Point being, chemistry to a large degree is about understanding molecular bonds, right? Bonds between atoms and a molecule. Where do molecular bonds come from? Well, they come from the behavior of electrons, as it turns out. And electrons have to satisfy some fundamental rules. And the fundamental rules that electrons have to satisfy, one of them is called Schrodinger's equation. And Schrodinger's equation, big, complicated, nasty-looking thing, Schrodinger's equation involves this symbol called the Laplacian operator, which is an object of multivariable calculus. So you have no chance of understanding, of understanding to this extent how molecular bonds work and where they come from without understanding multivariable calculus, because again, it's one of the participants in the story. Okay. Alrighty. Questions about this one? And the difference between this and the previous example, this we're not going to actually study in this course, but here we go. But this Maxwell stuff we will. All right. So this is a lot of examples, field-specific examples of how multivariable calculus comes up, not only in sort of what you might call fundamental, easy ways, but also in powerful and deep ways, right? Understanding mathematical models of economic scenarios, understanding E&M, understanding quantum mechanics. All of this hinges on, among many other things, multivariable calculus. So I like to phrase it as follows. I think this is a good little pithy summary, but multivariable calculus is the calculus of the real world. Single variable calculus is a special case when you assume all sorts of convenient, usually unrealistic assumptions. But in reality, most of the time, outside when nothing is working out nicely, multivariable calculus is what things really need. So that's why we're here. That's why your major, presumably, is requiring you to take this course. Everybody happy with that explanation? All right. Okay, so moving along. Now we're going to get into the book. And I'm now realizing that I am real low on power. That's scary. It says I have 40 minutes remaining. We have 20 minutes left in class. Looks like we'll make it. I don't know how my power level got that low. I'm going to have to bring my power cable next time. Okay, starting with Chapter 1. I said some of this in the recording y'all have already listened to before class started. There's tremendous amount of material in this class. It's ridiculous how much material there is. There's no way that I could talk about all of the topics and all of the examples and all of the applications. There's not enough minutes. There's not enough time to do it. So I have to make some tough choices. as to what I spend class time on. It remains that you're responsible for all of the material. Of course, keep in mind, we do have the content syllabus documenting exactly what from the book you're responsible for. If it will come up any second now. Dramatic pause. There we go. Here we go. Okay. So, which sections, what additional stuff, what stuff you can exclude, right? You're responsible for all of that, independent of whether I talk about it in class. And in class, I'm going to make these tough choices and talk about the things I think are the best use of class time. And this comes in different categories, by the way. To some extent, I'm looking for the material that's the most important, but it's not just that. It's also the material that is most confusing, that you need the most help to understand. And then there's the material which understanding benefits most from seeing a visual, in-person, explanation, with words and drawing and stuff like that. That's just so much more luxurious than trying to read out of a dead book, right? Complicated, tough choices I'm going to be making in terms of what we actually spend time on. Chapter 1 has a lot of stuff that you've, I believe, already seen in Math 218. Much of it you have not, and we will spend time on that stuff. But the stuff that you've already seen, and also, furthermore, some stuff that I think is a pretty easy read. That stuff I'm going to leave to y'all to read on your own. And I'm instead going to spend that time on the more sophisticated, the more challenging material from the later chapters. So anyway, heads up, while this is true for all the chapters, at least to some extent, it's particularly true in Chapter 1. There's going to be a lot of stuff that you're going to have to read on your own, and a lot of it just as review, but also some of it as, yes, you need to know it, but it didn't make the cut on valuable class time. Okay, so now I'm going to start with section 1.6. That seems weird. I just have a different point of view than the author of the book as to what the first topics ought to be. To some extent, it's related to the fact that this course has a linear algebra prerequisite, right? And so I want to cover the linear algebra first. And chapter 1 is largely about linear algebra, and 1.6 specifically has some just straight up Math 218 material in it. Okay. So starting with 1.6. First, something that you probably haven't seen before, based on what I understand from the earlier classes. This thing called the triangle inequality. You may have seen it, but anyway, you might not have. Triangle inequality, you can see why they call it that. Right? When you add two vectors, the picture that results is, it forms a triangle. So the triangle inequality says that if you look at the length of that vector, and if you compare it to the sum of these two lengths, right, that the shortest one is the straight line. And so I think this is very naturally thought of as thinking of these green and light blue lengths as being alternative paths between these two dark blue points, right? So if you ask the question, if I want to go from here to there, what's the shortest way to get there? Well, the shortest way to get between 2 points is a straight line. Geometrically, I think that's highly believable. I hope that's highly believable, and it's certainly that's a very natural interpretation of this result. Everybody believe it? Now, to the question of how you prove this mathematically, I'm not going to spend class time on that because it's linear algebra, and that's it. So it's really, this would be a good Math 218 question, depending on how much time they spend talking about dot products and magnitudes and stuff. But there is a clever sort of point of view that you can take on dot products that will allow you to conclude the triangle inequality. And you can play around with it if you like. If you get stuck, I believe the proof is in the book. If it's not, or if you can't find it, or if you can't understand their argument, come talk to me in office hours. I'll be happy to show you how this works. But again, it's really a linear algebra thing, and so not what we want to focus on. Okay. Alrighty. Next thing you have seen before, I feel sure, and that is how to multiply a matrix times a vector. The thing is, there are different ways to multiply a matrix times a vector that have different advantages and disadvantages in different contexts. And I want to make sure you've seen the one that I think is the most important because of its, where its advantages lie. So the formula that I think most students have seen first, and that most students tend to gravitate towards, is what I'll call the dot product formula. And I think you all know what I mean. You dot product, the rows of the matrix with the vector that you're multiplying it by, and those dot products give you the coordinates of the vector. So that formula is fantastic if what you're facing is a matrix where you know all the numbers in there, and multiplying by a vector where you know all the numbers and you need to numerically do the actual arithmetic. Then that formula is super. The thing about it is, that's rarely the case. If it is, use a computer. You don't need to, y'all's job when you get out of Duke is not going to be to sit there and do that arithmetic, right? Y'all's job, what you can do that a computer can't do, is understand ideas about, for example, matrix vector multiplication, and use those ideas to connect to other ideas and do idea thinking, right? So what I like about this point of view here is that it's more idea oriented, and it tends to, as it turns out, connect to other ideas more than the other. So here it is. Oh, let me switch my colors here. Okay. A matrix vector product is a linear combination. Already I like this better than the dot product point of view. Just from this mere fact here. Because this formula, this point of view here is telling me directly what the matrix vector product is. Matrix vector product, linear combination. If you look at the dot product point of view, it's not directly telling you what the matrix vector product is. It's telling you how to compute its coordinates. That's pretty indirect, right? So this is telling you literally what that matrix vector product is. So right to the point. Okay, what's it a linear combination of? It's a linear combination, there it is. It's a linear combination of those things. What are those? Those are the columns of the matrix. And what are my coefficients in this linear combination? Well, let's see. The coefficients, here they are. They're these numbers. They're the coordinates of the vector. So that's how you interpret that formula up there. I think this is a really nice point of view. We're going to make explicit use of this point of view to prove a big theorem in a couple of pages, assuming my battery holds up. And it also gets used in other ways in multivariable calculus. So anyway, I want to make sure everyone has seen this, specifically this formula for matrix vector multiplication. Okay, and you might want to review some of your Math 218 notes on this topic as well if you have them. Okay, linearity. One of the fundamental ideas of linear algebra, arguably why they call it linear algebra, right, is because it's a study to a large extent of functions that have this property called linearity represented by that equation. So very fundamental to linear algebra. Make sure that you're clear on this. Now, the way I like to think about linearity is that if you do a linear combination, you'll notice here on the left side I'm doing the linear combination before I plug in t. Here on the right side I'm doing the linear combination after plugging into t. And the idea of linearity is that you get the same thing whether you do the linear combination before or after. Either way, same thing. So anyway, that's one point of view on it. Don't forget, of course, there are equivalent formulations of linearity. Equivalent because any function that satisfies one satisfies the other two. And so use whichever of these is most convenient depending on the circumstances. Notice that this has to work for all linear combinations, in other words, all real number coefficients, and no matter what vectors in your domain you're looking at. Okay. Oh, now, real quick, I'll point out, we're going to focus in this class on what I like to call Euclidean functions. Euclidean functions because, look, this is a Euclidean space. It's Rn, right? And this is Euclidean space. It's just Rm. It's just regular old vectors, right? Nothing spooky or weird. So I call this a Euclidean function, and so this is a Euclidean linear transformation. Yeah.
What is Euclidean?
Euclidean is just a reference to vector spaces that look like this, where the vectors themselves are ordered in tuples. You know, like R2 is the xy plane, for example. So that's doubles x comma y, ordered pairs. Does that make sense? Yeah. Yeah. So things get weirder when you're talking about different kinds of vector spaces, like vector spaces of functions or vector spaces of matrices or something like that. Then the definition of linearity is ultimately still the same, but for this class we're going to focus just on this. Yeah. Okay. Anybody else? All right, so a couple of examples, and again, I hope you all have seen this kind of thing before. Loosely speaking, this first one says that dot product is linear. Let me be careful to flesh that out. Here's what this function p does. P says, take some fixed constant vector A. The function p says, whatever input you give me, I'm going to dot it with A. Right? So the input here, x, I'm going to do what the p function says. I'm going to dot it with A, and that then gives you the output value of the function. So the blue x vector goes in, the purple dot product is what comes out. All right, is everybody clear on what this function is? Okay, this function p is linear. Now that's something that you can prove. The way you're going to prove it is by just using this property. Just, start with the left and use known established properties of dot products to rewrite it as the right. Okay. All right. So so this is a dot product. This dot product function is a linear transformation. Likewise, the cross product. Come on. The cross product, namely, give me a fixed constant vector A, and then whatever input value x you give me, I'm going to cross it with A. Right. So this function C is a linear transformation. Is a linear transformation. Okay, how we doing? All right. Okie dokie. Next one's a little bit weird. Again, when you're talking about a function being linear or not linear or something like that, you do have to be very, very clear what the function is. So in this next one, you got to be very careful. There's an important subtlety here. The function you see here, it kind of looks like I'm talking about determinant. I'm not. Determinant is a function that acts on a matrix. That is not what my function D does. My function D, that I've got here, D says, yeah, you're going to take the determinant, but all of this is fixed. So all of these first several vectors that make up, the first however many rows here, all that's fixed. What D does is it says, if you give me a vector I'm going to make that the last row, and then I'm going to compute the determinant of the resulting matrix. So D, as I have it defined here, D acts on vectors, not matrices. Does everybody see the difference? Okay, yeah, question?
So, would you like to treat it like a normal determinant?
One more. I'm sorry.
Are you going to treat it like a normal determinant?
Oh, yeah. When you compute the determinant, yeah, it's the same. It's the usual normal determinant. It's just that I can't say D is the determinant of X because X isn't a matrix. So D acts on a vector X by first taking X and making a matrix in this very particular way, and then once you have that matrix, then yeah, you take the determinant. Yeah. Yes.
So it's just like saying that like basically the input of D is the vector X instead of saying is that okay.
Yep. The input to D is the vector X, and you make a matrix as indicated, take the determinant of that matrix. That's how you compute D. Yep. So, now, it would be wrong to say that determinant is linear. Determinant is not linear. Determinant, again, is not what I have written down here. Determinant is not D. Determinant acts on matrices, and it's not hard to find counterexamples showing that determinant is not linear, but D is linear. So, now, casual parlance, the way we describe this is, what people will say. This is a little sloppy, but there's a lot of math slang, and it's very convenient, and we're not going to stop it, so we might as well get on board with it. The math slang here is we say that determinant is linear in the last row. And when we say in the last row, that's the indication that we're viewing only the last row as being the input to our function. Implicitly, then, all the other rows have to be fixed. And as such, yes, this resulting function where only this one row is the input, that resulting function is linear. So determinant is linear in the last row. Now, also true, determinant is also linear in each of its other rows, which is weird. Determinant is a weird thing, right? So determinant is in fact linear in every one of its rows. Amazingly, determinant is also linear in every one of its columns. And altogether, the fact of being linear in every row and every column is called multilinearity of determinant. So I don't know if you've ever seen multilinearity before, but that's all it is. It's just saying that, pick one row or one column, but fix it. Once you've picked it, you're only looking at one row at a time. The resulting functions are linear. Okay. All right. I think this is a really important fact of linear algebra. I understand that Math 218 doesn't cover it, or at least not all sections cover it, so you may not have seen this before. They have to make the same tough choice as I do, and can't cover everything. Let's see here. I've got a minute and a half left. So at least it looks like I'm going to make it on the charge. That's good. I'm going to hit some quick highlights here about linear transformations being represented by matrices. This is a lovely little proof, and I want to hit the highlights of how this proof works. I'm getting ahead of myself. Here's linearity. You're assuming that you have a linear transformation. Notice here I have the linear combination on the inside. Here I have the linear combination on the outside. So linearity allows me to do that. The result then, is that I can rewrite t of x in this form. The claim that I'm interested in is that I can rewrite t of x as being some matrix A times x. Well, wait a second. What is AX? AX, recall, we've already talked about. It's a linear combination of the columns. So, if I want to claim, as I have here, that t of x is equal to AX, if I want to connect this to that, right, how am I going to go about how am I going to make the green hook up with the blue? Well, all you got to do is choose to let this be your first column of your matrix, et cetera, et cetera. Let this be your last column of your matrix. So just set up, define your matrix to be this, where the columns are the images of the standard basis vectors. And, well, there you go. Then the green hooks up with the blue, and therefore T of x is AX as desired. So this is a neat fact. Again, you may have seen this in linear algebra, but beautiful fact, every linear transformation can be written as a matrix. And furthermore, not only can it be written as a matrix, but here's the matrix. I mean, explicit formula. That's how you do it. That is the magic matrix that makes it work. It's the matrix where the columns are the images of the standard basis vectors. So really beautiful little argument. I know I had to go through that quickly in the interest of time, and I do appear to be out of time. I'm just going to make a reference here. Read this one little short little result here that basically says that compositions of linear transformations count as matrix multiplication. It's a good fact to know. You've probably seen it before. And we're good for today. Sorry to go over. See y'all on Friday. Have a nice day. Glad to have you in the class.
Thank you.
Yeah, sure.